All right, let's talk about how to compare sets, right? So if you haven't watched Lecture 9 yet, you need to go back and watch Lecture 9 before you watch this one. In Lecture 9, we talked all about sets, roster notation, set builder notation, all of that stuff. In this lecture, we're going to talk about how to compare sets. And obviously, you're not going to be able to do that if you don't understand about sets in the first place, right? So make sure you watch Lecture 9 if you haven't yet. But let's talk about comparing sets. So one of the ways that we compare sets is we talk about whether or not two sets are equal. And we talked about this a little bit in the previous lecture as well, in Lecture 9. But let's practice it a little bit more. So two sets, A and B, are equal if they have exactly the same elements. In this case, we write A equals B, right? So if A and B are equal, then we write A equals B. And if A and B are not equal, then we write A does not equal B. Now, we mentioned in Lecture 9 that the order that the elements are listed in doesn't matter. For example, the set red, yellow, blue is the same as the set yellow, blue, red. And an element only needs to be listed once in the roster. So if you have something like A, B, C, C, B, D, that's the same thing as saying A, B, C, D, because the B's and the C's just repeat, and you don't need to write them down twice. So let's look at a couple more examples of this. So let's see. It says, which pairs of sets are equal? And in part A, we have the set Facebook, Flickr, Twitter, Pinterest, Instagram, Vine. That's one set. And then the other set is Pinterest, Flickr, Instagram, Twitter, Facebook, Vine, Flickr, and Pinterest. So the question is, do they have the same elements, right? And at first glance, you might say, well, this set looks bigger than the first one, except that, I mean, you have some repeats, right? Pinterest was listed twice. Flickr was listed twice. The real question is, are there any elements in the first set that are not elements in the second set? Or are there any elements in the second set that are not elements in the first set? Because if so, then the sets are not the same. If not, and they have all the same elements, then they are equal sets. And I think that's the case here, right? You've got Facebook in both of them, Flickr in both of them, Twitter in both of them, Pinterest in both of them, Instagram in both of them, and Vine in both of them. So yeah, the sets are equal. So these sets are equal for sure. Part B. A is the set of all X, where X is a citizen of the United States, and B is the set of all Y, where Y was born in the United States. So are these the same sets? Well, no, because first of all, you can have your citizenship in the United States without being born here. There are lots of people who are citizens of the United States that weren't born in the United States. So there are going to be a lot of people in A that are not in B, right? And vice versa, right? You could be born in the United States, but then give up your citizenship because you're living somewhere else that doesn't allow dual citizenship or something, right? So you could give up your citizenship. So no, these are not the same sets, right? They're not the same sets. Okay. So that's what it means for two sets to be equal. Now, another way that we compare sets is we talk about set equivalence, right? And the way that works is we say sets A and B are equivalent, or a better way to say it, in my opinion, is to say that sets A and B are in one-to-one correspondence if their cardinal numbers are the same, right? So if the number of elements in A is the same as the number of elements in B, then we say that A and B are equivalent. The elements themselves don't have to be the same, okay? This just has to be the same number of elements. So let's see if we can figure out which pairs of sets are equal and which ones are equivalent. So in part A, we have the set ABCD and the set DBACDC. Well, let's see. A is in both sets, B is in both sets, C is in both sets, D is in both sets. And then does this set have any letters that are not in here? C is there, D, C, A, B, D. So no, right? They have the same exact elements, and so these sets are equal, right? These sets are equal. Now, any set that's equal is also equivalent, right? So as soon as you're equal, you're equivalent, right? And that might seem, that's a little bit confusing at first, because you might say, well, but doesn't this set have 1, 2, 3, 4, 5, 6 elements, and this one only has 1, 2, 3, 4? But remember, an element only needs to be listed once in the roster. And so if you rewrite this and get rid of the repeats, you would have D, B, A, C. D we already wrote, C we already wrote, right? And then you would see, oh yeah, it really does only have 4 unique elements, right? So the sets are equal, therefore they're also equivalent, right? So if 2 sets are equal, then it's automatic that they're equivalent. The other way around doesn't work, though. So in logic speak, we would say, if the sets are equal, then they're equivalent. But it's not true that if 2 sets are equivalent, then they're equal, right? So, and part B is a good example of that. So part B, we have the set 1, 2, 3, and 4, 5, 6. Clearly, these sets are not equal because they have different elements, right? So these sets are not equal. However, they are equivalent. Right? Because they both have 3 elements. Right? They are equivalent. Right? They both have 3 elements. Ooh, went off the page a little bit, but they both have 3 elements. So they're equivalent, but they're not equal. Okay? And then finally C, we have the set 1A5 and then the set 1AB5. Well, the sets aren't equal. This set has B in it and this set doesn't. So the sets are not equal. They're also not equivalent because neither of them has any repeats, and this set has 3 elements and this one has 4. So these sets are not equal. We'll say these sets are neither equal nor equivalent. Okay? All right. So hopefully that helps you understand the difference between equality and equivalence, right? They don't mean the same thing. So try not to use them interchangeably because they're not interchangeable. Okay, another way that we compare sets is we can talk about a concept called the subset. All right? So let's say that A and B are sets. Okay, we say that A is a subset of B if and only if every element of A is an element of B. Okay. Another way to say that is A is a subset of B if, well, I don't know. I was about to say pretty much exactly the same thing. But yeah, like all of the elements of A have to be an element of B in order for A to be a subset of B, right? Now, if A is a subset of B, then we use this symbol. We say A is a subset of B. Okay. So they're not equal, but A sort of fits inside of B, you might say, right? So for example, if A equals the set 1, 3, 5, and B equals the set 1, 2, 3, 4, 5, then A is a subset of B, since 1, 3, and 5 are all elements of B, right? Right? 1 is in B, 3 is in B, 5 is in B. So every element of A is in B. Okay? Note that B is not a subset of A, right? right? For example, um, 2 is in B, but 2 is not in A. So not every element of B is an element of A. Okay. Okay. Now, on the other hand, if C is the set 1, 3, 5, 7, and B is the set 1, 2, 3, 4, 5, then C is not a subset of B. Okay? C is not a subset of B. Why? So pause the video and see if you can figure out why C is not a subset of B. Okay, so here's my answer to that question. Look, 1 is an element of C. It's also an element of B, so that's okay. 3 is in B. 5 is in B, so that's okay. But 7 is an element of C. That's not an element of B, and therefore C is not a subset of B, right? Since 7 is in C, but 7 is not in B. Right? So that means C can't be a subset of B. Notice that, again, B is not a subset of C either, so it doesn't work the other way around either. Because, for example, again, 2 is in B, but it's not in C. Okay. So at this point, maybe we should say, okay, so we're throwing around these symbols. We introduced the element symbol in the previous section, and now we've just introduced the subset symbol. And it's easy to get confused between those two symbols, but try to remember, try to commit this to memory, right? We use this symbol if we're trying to say that an element is contained in a set, right? And it looks like an E, so you can think E for element, right? We use this symbol if we're trying to say that an entire set is contained in another set, right? So we use the subset symbol if we're trying to say that an entire set is contained in another set. So, some examples, right? So we've got 3 sets, A, B, and C. And let's see if we can fill in the blank with the appropriate symbol, either the element symbol or the subset symbol, or maybe element symbol with a slash through it if it's not an element, or a subset symbol with a slash through it if it's not a subset. So part A says 2 blank A. Well, we don't have curly braces around the 2, and so we're not thinking of this 2 as a set. We're thinking of it as just a number, just an element. And so 2 does happen to be in the set A, so we would say, yeah, 2 is an element of A. Now contrast that with part B. Part B has curly braces around the 2. So now we are thinking about 2 as a set. And so we wouldn't say 2 is in A. We wouldn't say the set 2 is in A. That's not true at all. We would say the set 2 is a subset of A. Okay? You could imagine a scenario, maybe, where you have some set, we'll call it A star, that's made up of 2, 3, the set 2, and then 4, or something. Here you could say that the set 2 is in A star, right? Because the set 2 is an element of A. But here, the set 2 is not listed anywhere, right? So it's not correct to say that it's an element of A. But you can say it's a subset. You can say it's a subset of A. Okay. 1. Again, no curly braces, so we must be talking about an element. But it's not an element, so the correct symbol would be to say it's not an element. Okay? Part D, we have curly braces around the 1. Now we're thinking of the 1 as a set, but it's not a subset of A, so we would say it's not a subset. 3, 5, and 7. There are no curly braces around this, so we're thinking of each of these as elements, 3, 5, and 7. They are all elements of B. So we would use the subset, or sorry, the element symbol E. They're all elements. Here we're comparing the two sets B and A. So let's see. Is B a subset of A? 1 is in B, it's not in A. So automatically I know that no. But since we're talking about sets, we would use the subset notation and say no. In part G, we have the set 3 and 8. Yeah, 3 and 8, yeah, that's a subset of the set C, because 3 and 8 are both in C. Okay, and then finally we're comparing C and A. So 3 is in C, it's in A. 5 is in C, it's in A. 8 is in C, it's in A. So C is a subset of A. Okay. Moving on. So here's something about subsets that may be a little confusing, right? But sets that are equal are considered to be subsets of each other. For example, if A is 1, 2, 3 and B is 2, 3, 1, then A equals B, right? They're equal sets, right? They're equal to each other. But we could also say A is a subset of B, right? That would also be a correct statement. In fact, we could also say B is a subset of A. Right? These are all correct statements. Okay? So if we want to say that one set is a subset of another set, but that they're not the same, then they're not the same set, then we call that a proper subset. So we say the set A is a proper subset of the set B if A is a subset of B, but A is not equal to B. And in that case, we just use this symbol. We say A is a proper subset of B. If A is not a proper subset of B, then we say A is not a proper subset of B, right? So, for example, the set 1, 2, 3 is a subset of the set 1, 2, 3, right? But it's not a proper subset. Set 1, 2, 3 is not a proper subset of the set 1, 2, 3 because they're the same set, right? In a proper subset, the sets can't be the same thing, okay? Also, clearly, 2, 4 is not a subset of 1, 2, 3. So it's not a proper subset either because 4 is an element of this set, but not an element of this one. On the other hand, we could say the set 1, 2 is a subset of 1, 2, 3. We can also say 1, 2 is a proper subset of 1, 2, 3. Those would both be correct statements. Okay. So let's look at another example. This one says, consider the following table of medalist winners at the 2014 Winter Olympic Games in Sochi, Russia. Okay. And then it says, assume that this set... So we have the names of the athletes, the event that they did, the medal that they won, gold, bronze, or silver, and then the country that they're from, right? It says, assume that this set is the universal set and define the following sets. Well, first of all, what do we mean by the universal set? I should have written this definition sooner, but the universal set is the set of all elements under consideration in a given discussion. And we usually denote the universal set with the letter U. So when this says, assume that this set is the universal set, what we're saying is that we're assuming that these are all of the athletes that exist, right? We know that there are other athletes in the world, right? But these are the only ones that we're going to consider for this example. And so this is the universal set. Okay? All right. So now, assuming this is the universal set, it says define the following set. So S is the set of all slalom medalists. A is the set of all U.S. athletes. G is the set of all gold medal winners. N is the set of all Norwegian athletes, and B is the set of all bronze medal winners. Okay? It says, which statements are true? So statement A says A is a subset of G. So A is a subset of G. In order for A to be so A is the set of US athletes. US athletes. So that would be this person, and this person. A is a subset of G. So in order for A to be a subset of G, we would need for all of the elements of A to be elements of G. Well, what's G? G is the set of gold medal winners, right? So G would be this, and this, right? So the question is, are there any elements of A that are not elements of G? Because if so, then A is not a subset of G. And in this case, I think there is one, right? This person right here is a United States athlete, is a US athlete, but she's not a gold medal winner, right? So this is false because Hannah Kearney is a US athlete, but not a gold medal winner. Okay? Okay, part B. N is a subset of B. Maybe I'll do this one in a different color. N is a subset of B. Well, N is the set of all Norwegian athletes. So N would be if they're from Norway. So that would be this person, and I think that's all the Norwegians. B is the set of bronze medal winners. So where are my bronze medal winners? So that's this person, and this person. Okay? So is it true that the set of Norwegian athletes is a subset of the bronze medal winners? Yeah. Right? This person, Henrik Kristoffersen, is Norwegian and he's a bronze medalist. Martin Sundby is a Norwegian who is a bronze medalist. And there are no other Norwegians listed. So all of the Norwegians were bronze medalists. This is true because all of the Norwegians were bronze medalists. Okay. And then part C. Part C asks, is N a proper subset of B? Well, in order for N to be a proper subset of B, we need for N to be a subset of B, which we know it is, but then we also need N and B to not be exactly the same set. And they're not, right? Because B has Hannah B has Hannah Kearney in it, and N does not. So that means that they're not the same set. So N is a subset of B, but N is not equal to B, and so N is a proper subset, right? So this is true because N is a subset of B, but N is not equal to B. Right? Hannah Kearney is an element of B. Right? She was a bronze medalist. Okay. Very good. So that's that. Universal set we talked about, right? It's the set of all elements under consideration in a given discussion, and we usually denote it with the set U, or with the letter U. A Venn diagram. You've probably seen Venn diagrams in the past, and they're very similar to Euler diagrams, which we've looked at in this class already, right? But a Venn diagram is a picture that visualizes sets as circles or ovals within a universal set represented by a rectangle. So here's how we would visualize A as a subset of B as a Venn diagram. So first of all, you would give yourself a rectangle that represents the universal set. And then if A is a subset of B, that means that all A are B, right? All A are in B. So you would draw a circle representing B, and then inside of that you would draw a circle representing A, right? So that means A is a subset of B, right? If you had a situation like this, where maybe this is B, this is our universal set, and then this is A. Here, A would clearly not be a subset of B, because there are going to be some elements of A that are not elements of B, right? And of course, there are other ways that A could not be a subset of B, like you could have the situation where they're completely disjointed, right? So B and A. This would also be A is not a subset of B. I'm sure there are other ways that you could kind of get that scenario, but the point is, this is how you would visualize A as a subset of B using a Venn diagram. Okay. Another thing to say about subsets is we might be interested in listing off all of the subsets of a particular set. And one thing to point out right off the bat that's maybe a little bit not obvious is that every set is going to have at least two subsets, right? The empty set and then the set itself. I guess that's not quite true because there is one exception, and that is the empty set, right? The empty set only has one subset, and that is the empty set, right? But any other set is going to have at least two subsets, the empty set and the set itself. So if S is a set, then we consider both S as a subset of S and empty set as a subset of S to be true statements, right? So we sometimes want to know what all of the subsets of a set are. For example, what are all of the subsets of the set 1, 2, 3? Well, first of all, we just said the empty set is always a subset of our original set. In addition to that, we could look at all of the singletons, like the set 1 is going to be a subset of this set. The set 2 is going to be a subset. The set 3 is going to be a subset. So those are all the singletons. All of the pairs are going to be subsets. So like 1 and 2 is a subset. 1 and 3 is a subset. 2 and 3 is a subset. I think that's all of the pairs. And then finally, the entire set is a subset of itself. So the set 1, 2, 3 is also a subset of that original set. Okay? So that's true of this set, and this set had 3 elements in it. Any set with 3 elements is also, so notice that there are 1, 2, 3, 4, 5, 6, 7, 8 subsets, right? So there are 8 subsets in total. And that's going to be true for any set with 3 elements, right? Any set with 3 elements would also have 8 subsets. So instead of 1, 2, 3, you could call them A, B, C. And then you'd have the same scenario, empty, A, B, C, A, B, A, C, B, C, A, B, C, right? And you'd get 8 subsets. Okay, so any set with 3 elements has 8 subsets. Well, what about a set with 2 elements? How many subsets would it have? What about a set with 1 element? Or what about a set with 0 elements? Well, let's look at this, right? The subsets of the set AB would be empty set, singleton containing A, singleton containing B, and then the entire set AB. So that's 4. What about just the singleton A? Well, the subsets of A are going to be empty set and then the set itself. right? So 2 elements there. And the subsets of the empty set are just empty set, right? So note the pattern. If your set has 0 elements in it, like the empty set, then it's going to have one subset, namely the empty set. If your set has 1 element in it, then it's going to have 2 subsets, the empty set and then the set itself. If your set has 2 elements in it, then it has 4 subsets, right? And if your set has 3 elements, then it has 8 subsets, right? So this is the chart that we get. Notice that 8 is 2 cubed, 4 is 2 squared, 2 is 2 to the first, and 1 is 2 to the 0. So if you have 0 elements, you have 2 to the 0 subsets. If you have 3 elements, you have 2 to the third subsets. If you have 1 element, you have 2 to the first elements or subsets. And in general, a set with k elements has 2 to the k subsets. Right? This is useful for us. So let's say, for example, that you wanted to know how many subsets of this set there are. So how many subsets of the set A, B, C, D, E, F, G, H, I, J are there? Well, that's easy, right? So you count up the number of elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so you say there are 2 to the 10th elements. What is 2 to the 10th? I'm going to use my calculator. 2 to the 10th is 1024. We probably don't want to sit here and list them all, right? But at least we know that there are 1024 subsets of this set, which is kind of mind-boggling, right? But there you go. And that'll do it for comparing sets.